All right. So here's where things get really, really interesting. Hey, can I find my pen? Where did I put it? Oh. See, can I use my finger? Maybe not. There it is. Pens always roll under the weird side of things. All right, so the main key, what makes this type of statistics and statistics in general and how we infer from statistics is the central limit theorem. And what we're going to say is it's going to have a couple rules. If the sample sizes are of n greater than or equal to 30, and this number has a reason, and you'll see later on when we study t-distributions where this might mathematically be coming. It's not directly related to that idea, but there's something about the shapes of any distribution that when we get to a certain size, we can start making the assumption, and 30s are cut off. And so I like big N. I'm a big N person, and the central limit theorem holds for me. When you have less than 30, then we have to do some things. But this is drawn from any population, and the population has a mean mu. Now we might not know what that is, and a standard deviation, which will be sigma, right? And then I said we use Greek to denote our population's mean and standard deviation. Then the sampling distribution approximates, and so we'll say it's the estimate that for that and so the greater the sample size, the better that approximation. And the book does a really good job of, my population could actually look like this. Right? I do a frequency of count everything up, and it's nasty, it's curved. But I can measure this data will have numbers, right? When you did the parking tickets, it was, right skewed, had a hump over here, a side hump over here, but it still had a standard deviation, and it still had a mean that described this data. One of the things we can try to do is we can try to break it into sections, or other things we can do with it. We'll learn more of those as we go along. But if this is bigger than 30, and there's a standard deviation here, then in the estimate, we can estimate the population mean with our sample means, our sampling distribution means. The other case is if the population itself is normal. If the population is normally distributed. And that might sound, well, how do I know if a population is normally distributed? Well, theoretically, a lot of things are normally distributed. How the population comes to be, how it grows, the sociological methods that scatter people out, the physiological nature of things, or even just the physical processes that cause something to come into being, often follow normal distributions. There is some true value, and small differences cause slightly more, slightly less, usually never skewing it more. So if our population is already normally distributed, right, it's got a standard deviation in it, and it has a mean. And we can say, hey, our population, our sampling distribution will estimate this well. And our sampling distribution will usually be tighter, and it's going to have the standard error. for it. And the standard error. And this gives us ways that we can talk about it. And so if the population is normally distributed, this estimator is good no matter the size of n. And so in either case, sampling distribution has a mean equal to the population mean, and we have this relationship for standard deviations. And that's the central limit theorem. It says if these things obey these rules, then we're going to be able to make these estimates. So let's do an estimate here. A study analyzed the sleep habit of college students. The study found that the mean sleep time of the college students was 6.8 hours with a standard deviation of 1.4 hours. If we take a random sample of 100 sleep times drawn from this population and the mean of each sample is determined, find the mean and standard deviation of the sampling distribution means. So, well, I have a large n. So the central limit theorem tells me that my sample mean is approximated nicely, and so I should see around 100 hours. Or not 100 hours, 6.8 hours in my sampling distribution. Now, the standard error of the mean, the distribution's standard deviation that I'm going to see in my samples, not the population. Okay. And notice we're knowing things about the population in this. And so I have 1.4 divided by the square root of 100. And my square root of 100 is 10. So that's 0.14. And so I should have a tight sampling distribution coming across from it. And that's what the central limit theorem does. Alright, let's go to another example here, because there's some neat stuff we can do through this. Kind of walking through the slides. Remember, I put the slides up there, and you can work your way through. Well, we can transform our sampling distribution mean to a z-score. I can take my sample, right, some population, and I grab a sample of it. I grab this bit here, and I find its mean. Well, I can turn that to a z-score. And just like the z-scores we had before, I take the average of a sample, right? Because remember, there's a sampling distribution, a sampling distribution, a sampling distribution. And I subtract it from the average of all sampling distributions. And I divide it by the standard deviation, standard error of the mean. And I know this equals something else. So I can also substitute that back in. I also know that that's going to be the population mean. And so I can do this. So I can have one sampling distribution, one of them, with a large n in it, and I can compute its z-score. And so notice I'm now talking about z-scores, and I can talk about them in slightly different ways. I have a sampling distribution, one individual sampling distribution's average, minus the average of all my sampling distributions. Well, if this is an estimator of the population, I can take one sampling distribution, and I can subtract it from the mean, the average of one sampling distribution, and divide it by the standard error, and I get a z-score. So let's use this in practice. So we're taking things we've done before, and we're now taking, I have measured data, I have seen data, and when I take the data I've measured and I get data out of it, I get its mean, I get its standard deviation of the mean. What does it tell me about the population? So, let's say I have some data here, and we have the average miles driven per day by age group. So I'll put some age groups down here. Decadal age groups. Right. And then up to retirement age, because your book likes doing that. And this is how many miles per day. One of the things I try to see when I look at data, right? If I look at it, lower here, peeks through. And so we're going to randomly select from this group 50 drivers. And so this is the population standard deviation is 20.7. And I'm going to randomly select from that population 50 drivers. So n equals 50. Sorry, I wanted to make sure I had that number right. And so what is the probability that the mean distance traveled each day is going to be between 19.4 and 22.5? So what I'm saying is, I grab 50 people, what's the probability that they're going to be between this range of distance? And so I'm now talking about the probability that I get. If I look at some range of distance, converting that probability into something about what I've selected for my sample. And we're going to say, hey, that's about what we have in the population as standard deviations. You'll find we're going to learn to estimate the standard deviation of the population from what we do. So let's put our little formulae together. Well, for this particular age bracket, our mean is 20.7 miles per day. Or is it per day? Yes. Not day. Is it day? Yeah, each day. And what I need to calculate here is my standard error of the mean. And so that's the population standard deviation over the square root of n, or 6.5 miles divided by 50. Square root of 50, sorry. Wrote it, didn't say it. Which is roughly 9/10 of a mile. And so if I look at Z scores from that, Z1 is, what did I want? I wanted between 19.4, so we'll make that Z1 for that, and Z2 for this. That's going to give me the lower side, Z1 and Z2, and I should be able to translate those into areas under the curve. So 19.4, well, let me put the equation in here. So it's going to be, is my average 1 point minus population over the standard error of the mean. So 19.4 minus 20.7 divided by, well, I'll just write this out, 6.5 divided by square root of 50. And that's a nice little walk onto calculator land. It's negative because this is smaller than this, so it's going to be negative. And I get 1.41. Repeating that for the other end. And so it looks like these will be, if I want a better representation of it, I'm going to have one that's on my negative z-score side and one that's on my positive, because this is bigger. So I get 22.5 minus 20.7 again over 6.5 divided by square root 50, or 1.96. And so I want the probability that my z-score is between 1.41 and 1.96. And when we looked at a probability of z-scores like this, that was, if I draw on my graph, why I always like drawing on my graph, I get the probability of everything up to here, and then I subtract from it the probability of everything here. So if everything up from here, I'm going to get this little bit here, and I need to subtract that out. So I want my probability of z equaling 1.96 minus the probability of z equaling negative 1.41. Now we can look that up in the table. We can do the inverse z distribution that we did when we were looking at the probabilities coming here. But I'm going to look this up into the tables, and I get a 0.9750 minus 0.0793, or 0.8957, right? All right, and so we could do, z inverse functions. And the fact that we're using z-scores, then that means we're doing it with the assumption that the mean is equal to 0, or standard deviation is equal to 1, the mean is equal to 0, wrote the 1 symbol, said the other. If we were going to use those in calculations, and then these are the values we get, or we could look up the numbers on the table in the back of the book, whichever you're comfortable with. I tend to now use the inverse calculator. I was a table guy up until recently. And so that says that there's an 89.57% chance that of those 50 drivers, they're going to be within that distribution. Roughly 90% of the time they'll be within there. 10% of the time they won't be. All right, and so the central limit theorem and our sampling distributions connect our observed, or what we, to the population. If we know the population, we can see what we would expect to observe from the samples, and our key tool in all of these are the z-scores. And the z-score is our tool. And so the ability to go from x to z to probability, well, we can also go from probability to z to x. And that's going to actually help us start talking about something that we're going to do. And so in Chapter 6, we're going to change our language now. And so we've developed a means now that we can measure data, we can take samples, and we can now talk about what we expect the population to be. What are the odds the population will be based off of what we've seen? And I introduced the language here when I said if we're grabbing this sample, and we can say that there's a 89% chance that our data will be within a certain range. Well, that range, we're going to start saying we can talk about how confident our estimate is. So if I'm saying that the sample's average, the sample's mean, is going to be an estimate of the population mean, I'm saying I've observed something and it's telling me a truth about the population. Well, we're going to need to clarify that, because there is a probability that the data we did isn't capturing the mean. And so what we're going of the true value. And the language we're going to use is we're going to talk about how likely it is that our data, we're going to talk about the likelihood of our data. We're going to talk about how confident we are. We're going to talk about confident intervals. I'm 90% sure. And we can talk about our error, that these values are good plus or minus so many percent. And that's the proper language of statistics when we infer about the population. If I take a sample, I'm using the central limit theorem to estimate the truth of what I've measured, the true value, even though I haven't gotten it all. And so when we talk about it, we're going to need to talk about how confident we are. We're going to talk about our confidence levels. We're going to talk about our certainties. And so in chapter 6, we're now going to take this probability, we're going to take these probabilities of what we observed, and we're going to say we're going to be able to talk about how certain, the certainty we are that we measured the true value.